Okay, so today is our third and somehow last session on quantum computing. And what we are going to discuss today is Shor's algorithm. This is Shor's algorithm, and that's the algorithm for factoring. And that is from 1993. Okay, so to make a quick recap, so what we've seen so far is that one great thing you could do with a quantum computing device, with a quantum circuit, is to estimate some global property of a function. In particular, last time we discussed this algorithm of Simon, where you can find out the period of some function. And so that was a bit of a special case, because there we had a sort of Boolean function, so a function defined on bit strings. But however, you see, the general idea was that you had a piece of a quantum circuit that was good at doing a sort of Fourier transform. So that's what you have to do to find the period of some function. And so essentially what this person here, Peter Shor, realized was that finding the period of a function allows you somehow to solve the problem of factoring. Okay, so that is not obvious. So this is the first thing that we are going to discuss and see how that problem is related to finding the period of a function. So remind you, the goal is to find the factors PQ from the product. Okay, so you are given n, and you should find what are the products. So P and Q are prime. That's the promise. This is also the instance when this problem is hard. Okay, if these numbers are not primes, then there are other factors, and then it becomes much easier. And so the point is that that Shor's algorithm will do this in a time that is poly, so t will be poly log n. Okay, so log n is the essentially number of bits you need to describe this input here, and so this quantum algorithm will be polynomial in the input size. So what we are going to exploit is somehow, was there a question? Yes or no? Something beeped here, so I don't know what it was. Okay, no question. So factoring is equivalent to the problem of finding the period of a specific function. And of course, because factoring is a hard problem, this means that this is, so finding the period of this function, this is a hard problem classically. And indeed, because this is typically done via Fourier transform, and this is not an easy problem. So here is our specific function will be this one here. It will be a function that is defined with two parameters, n and some number a that we'll define in a minute. And it's defined on integers x. And this will be the rest of the division of a to the power x by n. Okay, so it's a to the power x mod n. And a, so a should be smaller than n, and A needs to be co-prime to n. Okay, so co-primes mean no common factor. So the idea is that the period, let's call it R, of this function f of a n depends on a and n. And so therefore, if you are able to find out what is this period, given that a will be a number that you choose, okay, when you do your computation, so then if you know the period, if you know a, then you will be able to find n. Then you will be able to find the factors of n, okay. So, okay, I won't go through the whole math of this because this is a bit too sophisticated given my my knowledge of number theory. But here is the main idea. So this is a theorem due to Euler. And so the point is that you see, so what we're going to say now is something that is sort of probabilistic, right? So because given our problem here, so given the n, we will have to choose some a and then compute this period of this function here and hope for the best somehow. So that means that this procedure is not going to work all the time. There will be choices of the parameter a for which it doesn't work, but there is a large chance of finding parameter a's for which it will work. And therefore that it will be one of the reasons why the whole thing is effective. So here is this theorem of Euler, is that, let me see what is the best way to write it. Okay. Okay, let's do like this. So essentially, the point is like this. So the probability that R is even and that a to the R over 2 plus minus 1 are not multiples of n. So the probability that both of these things together are true, this is always larger or equal than 1/2 for randomly chosen a, okay, and a smaller than n. Okay, so let's see why this is good for us. Because what we have is that, so in general, the point will be that we will have that a to the R will be equal to 1 mod n. Now, the point is because R, so you see, so if R is not even, then it's not good for us. So then we will go and pick another A. But if R is even, so if R even, then we can write, so this equation we rewrite as R A to the R over 2 plus 1 times A to the R over 2 minus 1. That should be 0 mod n. Okay, so what I did here is I put the minus 1 on the other side. Then A to the R minus 1 is 0 mod n. And then A to the R minus 1, I factor like this. Okay, and this is good for me. Well, I will need, I ask that R is even, right? Then I have actually numbers here, right? I want integers for these things. So let me call these alpha and this beta. So I know that n divides the product alpha beta. And so if now I have the second property that none of these things, so neither alpha nor beta is a multiple of n, well, then you see that there should be a, I should learn something about the factors of n from alpha or beta. So if alpha and beta are not multiples of n, then n should divide partially into alpha and beta. So the point is we compute the greatest common factor. So how do we write this? Well, let's see. So this is the greatest or the largest. Maybe I should say largest. This is the largest common factor of n and alpha, and then I will also do it for n and beta, which will give the factors, or at least one factor of n. Okay, so I guess this is pretty abstract, and yeah, I definitely agree, it's pretty abstract, but it's good to do an example to see how it goes. So let's do an example where our number to be factorized is 15, and we are going to choose an A. Okay, remember we have to pick A that is smaller than n and that is co-prime with n. So we are going to take A equal 7. But of course there are other choices. One could pick A equal 2, 4, 7, 8, 11, 13, 14. Okay, so here we can even enumerate all the possible choices of A that would work. I mean, that are smaller than n and co-prime to n. However, not all of these would work in terms of, then having this period of the function being even and so on. Okay, so we choose here A equals 7 because 7 works. And among these, there are quite, there's at least a half that work. So here is our function. This is f of 7, 15 of x. So this is 7 to the power x mod 15. Okay, so if I pick an x here, 0, 1, 2, 3, 4, 5, 6, 7, well, I can calculate the f of x, which is 1, 7, 4, 13, and then it starts again. So 1, 7, 4, 13, and so on. Okay. Well, okay, so here you can check, you just trust me, but this is the result of this function here. And so you see out of this, well, the period is r equal 4. Okay, so it's an even period, so this is good. So then what we have is that we have that 7 to the power 4 is equal to 1 mod 15. Okay, so this is another condition that we needed to have, and this we have, this is good. And so now this implies that 15 divides, so the following expression, so we had a to the r over 2 minus 1, a to the r over 2 plus 1. Okay, so these were my alpha and betas. And now, I mean, a is 7, r is 4, right? So I can compute these things. This turns out to be equal to 48. This turns out to be equal to 50. And now we have that the greatest common factor, yeah, sorry, I write in, this is in French here, but, well, in fact, is it greatest common divide? Maybe this is in English. Okay, but you understand what it means. So the greatest common divisor between 48 and 15, well, that is actually 3. And then the greatest common divisor of 50 and 15, that is actually 5. Okay? And so therefore it works. So we got the factors of 15, which very surprisingly turn out to be 3 and 5. Okay, so here you see somehow the entire machinery of this thing. So you see, of course, I mean, here it's something very simple. I can do it on pen and paper. But you see, typically what's going to happen is that this function here will have a period r that becomes very big when n becomes very big, right? So doing it as I did here to find the period, I can no longer do it later on because the period of this function will grow very quickly with n. Okay, so that's why I need some smart algorithm. Here it will be a quantum algorithm to figure out the period of that function. All right. So here, maybe just before we go on, here are some remarks. So in this procedure, all steps, they are, okay, again, in computer science jargon, they are easy. So they are poly log n, except the step of finding r. Okay, and this is precisely the, so finding r, this is what Shor's algorithm is going to do. And this will be, so this is a probabilistic algorithm, so we are going to do k repetitions. when the probability of success is equal to 1 minus 1 over 2 to the k. Okay, and this is independent. So this success probability is independent of n. So it's not guaranteed to work in one round, but we just need to do it number of rounds, and then we can make the error, the probability of error, arbitrarily small. All right, so let's move to the algorithm. So this is now the quantum algorithm. So we will start by drawing the circuit. It will have a unitary that implements the function we're interested in. It will have two registers as usual. One where we perform the Hadamard transform, another one where we do nothing. So this starts with 0. This starts with 0. And then, so here we are going to need a magic box, which is, we are going to call DFT. So that means discrete Fourier transform, and it will be represented by unitary. And here so in the end, we just measure. So we do measurements. Okay, so you see the architecture of the circuit is as usual. So we start in step 1. We have two registers. And these are registers of 2L qubits. And L here is equal to the input size. So this is log n. So maybe this is a little bit surprising, this factor 2. Why do we need to double the size? It will become clearer in the end. Okay, so for now I just highlight it, but I will explain it later. And so the initial state of our two registers is 0, 0. So then in step 2, we perform the Hadamard transform on register 1. And so therefore our state becomes now 1 over 2 to the L, sum over x from 0 to the power 2L minus 1, x 0. Okay, so remember the registers are of size 2 to the L. Okay, so here I have 2 to the 2L, but with the square root. And okay, here I have 2 to the 2L minus 1. All right, so now step 3. In step 3, we apply the function. So this is on both registers. And so therefore the state is 1 over 2 to the L, sum over x, and now I have f of a n x. So I encode all the values of the function in the second register. But of course we want now the period of this. And so at this point, it's useful to before introducing this new element here, it's useful to go back to our example. So our example, remember, it was n equal 15 and a equal 7. So if we, so now we are at this point here in the circuit, right? So we have just applied. So we have applied u of f of 7, 15. Okay. So what is the state that we have? So we have a state psi, and this state psi looks like this. Maybe I will not normalize it, but it will look like this. So in the first register, I have all the possible inputs, right? Because I applied the Hadamard here. And in the second register, I have the associated value of the function. So the first term is 0, 1, right? So 1 is the image of the function of x equals 0. Then I would have 1, 7. Then I would have 2, 4. Then I would have 3, 13. And then I would have, okay, let me continue here. I would have 4, 1, okay, etc. The period is 4, right? So at 4 here, I go back to the initial value of the function. Okay, so now let's imagine that we make a measurement here on the second register, okay? We are going to discuss why this part is important in a minute, but to understand that, it's good to imagine that we first do this measurement, okay? Okay, so now we do a measurement of second register, okay? And when we do that, well, what do we find? Well, we find only specific values now. If you look at this state here, right, the second register encodes the values of the function, and this function has period 4. So there are only 4 possible values, namely 1, 7, 4, and 13. And then it goes on, 1, 7, 4, 13, and so on. So here we find only 1, 7, 4, and 13, okay? So I mean, if we see only these specific results, I mean, here again, in our simple example, it's immediate to deduce the period. But in general, when the period will be large, this is not so easy. So now, what we are going to do is we're going to look at the first register. So here is what happens, and we make a little table. So this is the result of the measurement of register 2. Then we will have the state of register 1. And then I will introduce some notion I call the offset. Oops. So let me fill in this table here. So as we said, the measurement of register 2 leads only 4 results. 1, 4, 7, 13. So let's show this this picture here now. So if the result is 1, now we ask ourselves what would be the state of the first register. Well, let's look. So here I have a 1, so I have certainly a component 0. But of course I have another 1 here, right, because of the periodicity. So I have to add a term here with a 4. So plus 4. And of course, because of the periodicity, this goes on, right? So I have 0 plus 4 plus 8 and so on. Now, if instead of that the output was 4 for my measurement on register 2, okay, then the situation is different, because then you see with the 4, the state of the first register could be in the state 2. And okay, you see I didn't write everything here, but because of the periodicity of 4, it's obvious that here I have 6 and 10 and so on, right? I have again period 4, but now I start at 2. When the measurement of R2 would give me 7, it's the same idea, but now I will start at 1. So I have 1 plus 5 plus 9. And finally, when I have 13, well, then I the sequence starts at 3. I have 3 plus 7 plus 11 and so on. Okay, so you see that the periodicity I also see in the state of register 1, right? However, that periodicity I only see if I know what would be the result of measurement 2. Okay, because if I don't know the result of measurement 2, you see that all outputs are possible here, right? However, once I subdivide these into different categories corresponding to the measurements of R2, then I see the period appear, right? So somehow, what I need to, you see, what bothers me here is the fact that each of these 4 sequences has the period I want to find, but somehow, because they all start at a different point, if I just look right away at register 1, I cannot tell anything about the period, right? To tell something about the period, I would have to divide the data according to these different lines. And so what I would need for that is I would need to wash out this offset here. So here you see the offset. This is the starting point. Okay, it's the starting point of the sequence. Okay. So what we need, we need to get rid of the offset. Okay, if somehow I manage to always get rid of the offset so that the offset would be 0, then I would have only this first line here, okay? And if I would have only that line, then I can immediately find out the period, okay? All right. So for that, so what is the element that is going to do that? This is the discrete Fourier transform. Okay, so this last piece of element that we have in our circuit, this is the one that will do the job. Okay, so let's formalize this a little bit more. And so the point is that, so for any measurement result on the second register, on R2, R1 is in the state that is the following. So it's a state that is periodic. So let me write it like this. So this is a state that has a period. So let me write it. So, okay, so this will be the floor. In fact, it will be the floor of 2 to the 2L over R. And now this is J times R plus L. Okay, and there is some normalization in front, so maybe let me just put a wiggly line like this. So you see, okay, it looks a bit complicated, but in fact it's very easy. You see, this is a state here that has some periodicity, namely period R, right? Because each term here is a multiple of R with some constant offset L. Okay, so that quantity here, this is the offset. So it's easy to see that if you fix the value of the offset here to either of these four, then this superposition here is exactly correspond to these four sequences here, right? That's the correct thing. And so here the sum you see will go, I mean, so because here you pick only, you only have these periodic states here. And so among, remember you have 2 to the 2L terms, right? So essentially you need to look at 2 to the 2L divided by R, right? This is the number of times this number of terms you will have in this sequence. All right, so R is the period. And so now to get rid of this offset here, right, we will use this discrete Fourier transform. So let's discuss it. So now we talk about DFT. So let's define what this UDFT is actually doing. So UDFT, so UDFT acting on ket x, this is 1 over 2L y equals 0. So let me write it and I discuss it. Okay, so it's, you see, this is a y. Huh? So when I apply this discrete Fourier transform on some string x here, I essentially generate a big superposition, right, with all possible terms.
There is a problem with the phone.
Ah, yes, thanks. Thank you.
Thank you.
And so when I apply this discrete Fourier transform, I obtain this big superposition here. And you see these coefficients, they are somehow the Fourier transforms of x, right? So that's why this is a discrete Fourier transform. So if I want to make this a bit clearer, in fact, so if I would apply UDFT on some general state, so this would be, let me say that this would be, imagine I have a superposition now of all the strings x with coefficients cx. So this would become now a sum over y of coefficients cy, okay? Because now on each x I will apply this. So I will get something of this form. And so the point is now these cy, so these coefficients, these are the discrete Fourier transforms of Cx. Okay, and what this means is that Cy is 1 over 2L. It's the sum from x equals 0 to 2 to the L minus 1 exponential of 2 pi I xy 2 to the 2L Cx. Okay, so it's very reminiscent of a Fourier transform, and it's that thing, but somehow in a discrete manner. Okay, so now why is this DFT useful? So somehow the magic of DFT is to wash out the offset. Okay, and when I say wash out, what is in fact going to do, it will transform it to a global phase factor. Okay, so it will, if you want, the offset will still be there, but it will become some parameter that is physically irrelevant. So let's verify this. So we are going to look at the special case where R perfectly divides, divides exactly 2 to the 2L. Okay. So if that is not the case, the analysis is similar, it's just a bit more complicated. But the essence of the thing, you understand it in this case. So if that is true here, my output state is going to be the following thing. So it's going to be 1 over root R so the sum contains now R terms, and what I have here is 2 pi I L J over R, and then I have J times 2 to the 2L over R. Okay, so we will check this in a minute, right? I mean, this, you may say it's a bit out of the blue. At the moment, it is out of the blue, but we will verify it in a minute. But you see now, somehow the wonderful thing that happened is that instead of having let me put it here. So instead of having a sequence that is periodic and with an offset, and the offset being the annoying thing that we don't know, right? And that messes everything up. Now, after the discrete Fourier transform, so when we apply UDFT on this state here, let's call this our psi in. So if we apply UDFT on that state, we're going to get something like this. And now you see that state is great because this one has no offset, right? Here it is just J times that thing, and that is you see a new period, right? But there is no, here it's plus 0, right? There is nothing here, there is no offset. And you see there is still a dependence on L. So L was the offset, but now this is in this phase factor here, right? And you see the dependence on L is really just the same for each of these terms. So I can, you see, I could really pull it out of the state here and put it, it's really a global phase factor that has no physical meaning. Okay. So the point is, we started from some state psi in, which had period R plus offset. And then via the DFT, we obtain a psi out. And this has period 2 to the 2L over R and no offset. So one can even make a little drawing here. So if I could represent you see the coefficients of my input state. So these are the coefficients Cx. So here there would be an offset, and then I have something periodic here with period R, and so on. While now, after my discrete Fourier transform, I have coefficients Cy, and these things, they have now no offset and a period of 2 to the 2L over R. Okay, so of course this thing now is much better, because you see here the problem was that I didn't know the offset, and so in fact if I do not know the offset, then all possible outputs appear, right? Because all periodic patterns of R with different offsets are possible, and therefore this thing here would be completely homogeneous. While here, after the discrete Fourier transform, now I have only these specific peaks that have this so-called inverted period. Okay, so this, so 2 to the 2L over R, this is called an inverted period. And now, if I can determine the period of this output state, which is easy because now I have no longer an offset, once I know this, I can find out what is R. Okay, so once I find this, I can find R. And after R, I find the factors of N. Okay, so that is the general idea of how it works. And so for us, there is one so there is the main step somehow, which we would like to prove. And the main step is this equality here, right? And now we are going to prove this. Okay, so remember that we work in the case where R divides exactly 2 to the 2L. Okay, so I start by writing psi n. So here I write again a sum like this. And now, yes, okay. So now you see, because R divides exactly 2 to the 2L, well, then it means that 2 to the 2L over R is the number of different steps I have, right? And so therefore, this is the right thing here, okay? Good. So now this will be my input state, and this is what I call the coefficients X. Okay, so there is some periodicity in these coefficients X. And so let me see, can we write the coefficient here to be complete? So this would be just the square root of this number. So this is root of R divided by 2 to the L. Good. So now we go and compute the output state, and that is U dft applied on phi in. Okay, and that is going to be now of this form. So it's a sum over y, and y goes to 2 to the 2L over R, No, sorry, do I need to write this? Sorry, so this goes to 2 to the 2L minus 1. It's not very important, okay, but I think to get it right, we need this, because this is the size of the register. But what is important is the form of these coefficients Cy. Okay, so this we we will work out in detail. So let me see. So this is, so we still have our sum here. So here we have 2 to the 2L over R minus 1. Okay, because remember that in order to find the coefficients Cy, well, we apply this formula here now. Okay, that's the definition of the discrete Fourier transform. Okay, so this is, so that's why I have this sum here over J, right? And what I have in there is now the exponential of, this will be 2 pi I J R plus L times Y, and all that is divided by 2 to the, should be 2 to the 2L. Yes. Okay, and so, right, and so in front here I have a root R, so I have root R divided by 2 to the L, but now there is an additional factor from the definition of Cy, so I get a 2 here. Okay, now comes the main, and in fact only step, which consists in better understanding what is this thing here, okay? And we will argue that this thing has a very specific structure, actually. So here is how we do it. So we, okay, for completeness, we can put the coefficient in front. But you see, the first thing is that if we expand this sum here, right, we get a product of exponentials. And the second one is the one that contains the offset, right? So this one we are going to pull out. So here we have an exponential of 2 pi I Ly divided by 2 to the 2L. Okay? And then we have a term that is interesting. And this is the sum over J, 2 to the 2L over R minus 1, times now the exponential. And here, okay, I have the other thing that is left here. So it's 2 pi I J R Y over 2 to the 2L. Okay, and now, so you see this thing here, so you should understand these numbers as the roots of unity, right? The complex roots of unity of a certain order, okay? So, because indeed all of these are complex numbers that have modulus 1, so they are on the unit circle in the complex plane. But they are sort of, sorry, I should make it like this, right? They are equally distributed all around the circle, right? So they are the roots of unity of, you know, some order. And now the point is that you are summing these things, right? You are summing these roots of unity. And of course, when you do that, you know, eventually lots of things will disappear, right? So that's the idea on how we are going to evaluate this term. So let me let me show it here. Okay, I do it like this. So that thing here, this is going to be equal to 0, right? Unless you see that thing here is always equal to, I mean, unless that thing is equal to 1, right? For all j. So this is except if you have the following thing, if y is a multiple of 2 to the 2l over r. Okay? Because if that is the case, right, you see then you have something like, then you have an integer times 2 pi I, right? That thing here is now an integer. And if you have an integer 2 pi I, so you have, it's a multiple of 2 pi, right? The argument of this number. And so therefore it is always, I mean, if you have the complex, the unit circle in the complex plane, then you always have that number here, right? And so when you sum that thing, it doesn't go to 0, right? But if that is not the case, right? If y is not a multiple of this, then these things, they are sort of the roots of unity, right? So they will be distributed sort of evenly all around the unit circle. And so when you sum them, they shrink to the origin, right? So this is 0. So this is a sum of the roots, the complex roots of unity. Okay, so is that step clear? Okay, good. So now the implication is that my output state here, sorry, I should show it again. So my output state here, which is defined by these coefficients, this has a very specific structure, right? Because we saw that unless y satisfies a very specific relation, namely that y is a multiple of 2 to the 2l over r, well, unless that is the case, my coefficient cy will be 0, right? So it's only very specific coefficients cy that are going to survive. Okay, so I can write this out now. So the cy's are going to be the following thing. So they are going to be the exponential of 2 pi I Ly over 2 to the 2l. So sorry, why did I write this? Yes, no, okay, sure, this is good. This is good. But there should be an R, I think. No, but sorry, this is a bit silly, no? If y is a multiple of things. Okay, sorry, let me write it like this and we'll discuss it in a minute. So this is if y is a multiple of the 2l over r, and it's 0 otherwise. I don't understand why that thing, that thing should be equal to 1 somehow. Okay, let's figure it out in a minute, but I think it must be the case. All right, so this implies that indeed my output state is of the form that I announced. So it's the sum over, let's write k, from 0 to r minus 1 of the exponential of 2 pi I L k over r times k 2 to the 2l over r. All right. And so now there are r terms. So this here there is a factor 1 over r. That is correct. Is there a question? Okay, good. Yes?
Because L should be an integer. So the exponential of 2 pi.
So, sorry, can you say again? I didn't hear you completely.
Sorry. The 2r and L should be an integer. So the exponential should be 1.
Yes, I agree. Mm-hmm. Yes. All right. So I guess with this we are good. So in fact, so let me see, I have a note here. Let's check this. This is probably what we want. So my note is that this sum yes, okay. So this is of course a sort of triviality, but that is indeed true. And so that, so why does that enter now? Ah, yes, sorry. This is important because now I get the correct, so I have the correct factor in front, right? Because initially I had this coefficient here, okay, and then when I take into account all the redundancies and what goes and what is left, then indeed I find the right thing, okay? Because if I multiply this with this here, I find 1 over r, which is indeed the correct normalization. Okay, so this is why I have this note. Sorry, I got a bit confused with this. All right, so that's the general idea of this algorithm of Schur. So let's see. So maybe we can make a few comments of it about it. Sorry. So you see that really the main novelty here is this discrete Fourier transform, right? And what this discrete Fourier transform allows us to do is to get rid of this offset, and therefore this function here that had a periodicity in it, but an unknown offset, gets mapped to one that is periodic with no offset. However, what happens, you see, I mean, because we look in the Fourier space, right? So indeed, in the Fourier space, we can see the periodicity of that function. And now, of course, the point is the periodicity in the Fourier space is not the same as in the initial space. So we have this inverted period, right? Okay, so you see, so maybe to recap on the general procedure, it goes like this, right? So you are given an input n, you have to find the factors. So first you have to choose a number a that is co-prime to n, and be lucky that number of properties are satisfied. In particular, the period r should be even, right? But if you have that, so imagine you are successful, which Euler's theorem guarantees is something frequent. Well, then you go through this entire quantum circuit here. You find this inverted period. Okay, this is easy because now you measure at the output. And here, because the offset disappeared, you find very quickly this inverted period. And because you know L, then you find R, right? And from R, then if you are lucky, then you find the factors of L. And now you see, of course, something that is important here is that this inverted period might be in fact quite a bit bigger than R, right? And so that's why our registers of qubit need to be of size 2L, okay, not only of size L. So that's the sort of technical justification a priori why we needed this, right? All right. So unless there are more questions, we can stop here. So I see that it's not yet 3. So then what I would suggest to do is to reconvene in like 5-10 minutes and discuss, in fact, another algorithm, which is that of Grover, which is, quite a bit different than this one, but has advantages and disadvantages compared to this. But it's sufficiently different to make it interesting. All right, so see you in a little bit. And if there are questions, of course, I'm happy to answer.
I have.
Okay. Good. Paper. Okay, so now we move to the algorithm of Grover, which is from 96. And what this algorithm is about database search. Okay. So what's the problem? Sorry, the problem. So it's find an element in an unsorted database with n objects. Okay, so it's important that the database is unsorted, right? So when you look for the element, you have a priori no idea where it is, right? Could be everywhere. So of course this is a problem that is even more common than factoring, maybe. For instance, when you search some file on your computer. And so, well, you can immediately see that essentially, classically, the best thing you can do to solve this problem is that on average, you're going to need n/2 trials. Right, because you, view your database as a number of boxes. So you have n boxes. You are looking for, a marble. One of these boxes contains a marble, and so on average, you will need to open half of the boxes to find the marble. And now, so somehow the remarkable thing is that quantum mechanically, and this is the algorithm of Grover, you need only order square root n trials. Okay, and so there is a speed up, and the speed up is of a factor root n. Okay, so you see, conceptually, this is quite a bit different from the algorithms of Simon or even that of Shor, where the speed up is in principle exponential, right? But that is only if, under the promise that p is not equal to np, right? Or maybe weaker, yes, that would be necessary. And moreover, one would need to prove that factoring is not in P, right? So that factoring is not easy classically. But then you would have an exponential speedup for the quantum computer. Here it's a little bit different. The speedup is polynomial only, right? It's quadratic. But this is rigorously proven, right? So here, this thing does not depend on whether P is equal to NP. That speedup is a proven one, right? Because you see, classically, you can immediately convince yourself that this is the best thing you can do. Now, what is surprising is that quantum mechanically, you can do better. So let's see how that works. So we are going to have a set of different states that we call S0, S1, Sn, and these are n equal 2 to the L states. And now we have a condition, and this condition, we say this is C nu, and this is a sort of mathematical way for identifying one of these states. So this condition is such that C nu on the state S nu is equal to 1, and C nu on any other state, this would be 0. Okay, so for all I that is different from nu. And so our goal is we want to identify nu with a minimal number of trials. Okay, so here is how the algorithm works. So this is Grover's algorithm. So first we have a L qubit register. Okay, And so this is in order to, you see, that's why we needed the number of states to be a power of 2. Then it's more convenient. Right, and so our register is initially in the state 0, and so somehow the state x, this, well, let's say like this corresponds to the quantum state x. So now the second step in the protocol is that we apply the Hadamard as usual. So now we have a UH of x. Sorry, this should be UH of 0. This is 1 over root 2 to the L, sum of x. Okay, I don't write the indices for the sum. And then, so here comes the, I mean, this is the usual procedure, right? But here comes the main part of the algorithm, which you will see is very different than before. So you have to repeat order root n times the following operations. So first you apply UC new. Okay, so UC new, this is the condition that identifies the state, right? So UC new applied on new is the following. So you see it puts a phase factor in front of the state to be identified, and UC new on any other x will do nothing. And that is for all x that are different than new. Okay, so that is the quantum way of formalizing this identification condition. So this UC new, this is sort of a device or a box that, let's say, recognizes new. So then the next thing we do is we apply U of D, which is the following thing. This is U of H, U of C0. So this is UC0 is defined like this, right? And then U of H. Okay, so in fact it would be more from this side, U of H, UC0, U of H. Okay, so maybe I write it here, where UC0, again UC new for new equals 0. All right, so you repeat this thing a number of times, and at the end you measure the register. And so the claim is that now with probability of about 50%, we find new. Okay, so again, it's a probabilistic algorithm. You have to do it a couple of times, but you see that there is one output that will be quite frequent, while all the others are very unlikely. Right, because I mean there are lots of possible outputs for the measurement, and there is one that comes up with probability half, right? While all the others are with uniformly low probability. Okay, so that probably seems quite magical that this procedure works. So let's going to so we're going to try to explain the idea behind this. So the state of the register psi has the following form. So it's sorry, all these alpha x. So in all steps, there will be, we have a state of this form, right, which is a big superposition over all states, and there are some coefficients for each of these. Now the point is that, so here is the important thing. So this operation here, u of d, what it's doing is that it's doing an inversion. So by inversion, we mean flipping the sign of these coefficients. But it's going to be an inversion around the, so maybe say like this. So this is an inversion of coefficients Cx around the mean. Okay, and the mean is what? Well, the mean is, let me call it alpha bar. So this is 1 over 2L sum over x alpha x. So it's really the mean of these coefficients. Okay, so I was a bit quick before. You don't flip the sign of these things, but what you do is that you will invert these coefficients around the mean value of all the alphas. Okay, and maybe I should point out that all the alphas are real here. So flipping around the mean makes sense. Okay, so let's see how it goes. Again, we can understand graphically pretty well the situation. So initially, we start with something very uniform, right? And we are going to say that here somewhere is our element to be identified. So these are my coefficients alpha x. So this is at step 0, right? This is the beginning. Now what I do is I apply UC new, okay? And so now almost all coefficients here are unchanged, except for the one at new here, right? Which is flipped, right? This one takes now a minus phase factor. So now if I go here, I can draw the mean. Let me draw it in blue. So if I draw the mean now, it will be here, more or less, right? So this is alpha bar. This is the mean. Okay, it's almost at the level of these coefficients. It's just a little bit below because this one was pushed down. Okay, so now if I repeat this step again, now if I proceed with u of d, so I said u of d is an inversion around the mean. So let me draw the mean again here. It is here. So this is my alpha star. So now you see what happens is that, let me start first with all the uniform coefficients. These are slightly above the mean. So the effect of UD will be that they are slightly below the mean. Okay, they are like this. However, you see for the particular coefficient C nu, which was actually far below the mean, now it's going to shoot up far above the mean. Okay, so this is at nu. So you see somehow, okay, of course here I exaggerated the effect, right? But the idea is by doing this procedure, I'm sort of amplifying the difference between nu and all the rest, okay? So in each, you can see intuitively that if I repeat this thing many times, this difference here between this peak and all these uniform ones is going to become bigger and bigger. Okay, so now the point is that after that, my state has the form psi d, psi, and for all x that are different from nu, I have some constant factor. Give a name. No, I don't give a name. Call it alpha. But yeah, so my sum is here. But for the element nu, I have a different coefficient in front, right? So this state here reflects indeed this distribution. Now the point is, one can show that after j iterations, okay, the coefficient, this coefficient alpha nu, let's say in round j, okay, this is something like the sine of 2j plus 1 times some angle theta, okay? So for completeness, let me say that sine squared theta is equal 1 to the L. Okay, so somehow you see there is some interference going on, and when you iterate this procedure, this interference somehow builds up. So now let's look at different values of j. So at j equals 0, this is the starting point, so initial point. So here we have nothing special. So here alpha nu is just 1 over root 2 to the L. Okay, this is from the initial uniform distribution. Now turns out that there is a j, let me call it peak, and this is pi over 4 square root 2 to the L. Then for that one, alpha j is of the order of 1, okay? It's very close to 1. I mean, in fact, it will be such that the square of alpha nu here will be essentially 1/2. But the point is, if you continue, okay, so here you iterate. So if you would iterate more, you see your interference, which was maximally constructive at this point, will then become destructive. Okay, so then you decrease. So in fact, if you would double this time, if you would go to pi over 2 root 2L, okay, then alpha nu is essentially 0 again, right? Because essentially, you almost go back to the initial point, okay? And so then the point is, one should carefully choose the number of iterations. Okay, so you see also from that point of view, it's a very different type of algorithm than Shor's one. Okay, so I guess I will stop here. Yeah, so I would say these two algorithms, that of Shor and that of Grover, yes, they are some of the first, but probably the two most well-known quantum algorithms. And you see that both of them, they solve a problem that is not an artificial one, right? So factoring is important, for instance, for cryptography, in a sort of bad sense, because if you can factor efficiently, you can crack cryptographic codes. Nevertheless, it's nice to see that quantum mechanics also provides the solution to that with quantum cryptography. So because quantum cryptography is secure even against an adversary that would have a quantum computer, right? Remember, somehow to break quantum cryptography, the eavesdropper would have to break the laws of physics, right? At least the laws of quantum physics. So there is a nice nice trade-off here somehow between you know, the sort of cryptologic advantages provided by quantum information, namely the quantum computer, right? This is great for hackers, for eavesdroppers. But on the other hand, there is quantum cryptography, which is good for cryptographists, for people who would like to develop secure coding methods. And so then there is this other algorithm for this database search. You see, of course, that for all this procedure here to work, you need to have a database that is encoded in qubits, right? So you could not use this algorithm on any database, for instance, the one that you would have on your computer. So you need really a quantum treatment of the database, but then you can use all these ideas to speed up the problem of searching an element. All right, so I think I'll stop here. If there are more questions, I'm happy to answer. So if there are no immediate questions, I will switch off the recording.